All right. Uh, Good morning, good afternoon, or good evening, everybody. This is a tutorial on radiometry in general, and then more specifically spectra with respect to radiometry. Not a lot of people think about it, but radiometers, obviously, like many other remote sensing instruments, measure in very particular spectrum. Some of these are protected by government regulations, some of these aren't. And today I'll be giving a brief introduction on what radiometry is, specifically microwave radiometry, and then talk about how we are affected by the ever shrinking spectra, yet on the other side, how we're affected by the ever expanding needs for that spectra. I'd like to also acknowledge my colleague, Dr. Shannon Brown, who's also helped put some of these slides together for this tutorials for IMS. All right, so most folks listening in right now probably already know this, but just in case you don't, what's a microwave radiometer? These are very sensitive receivers that detect EM radiation in the zero point 0.3 to 300 gigahertz range. There are a variety of applications that I'll talk about up ahead. Um, and For the uninitiated, another way of thinking about this, many folks are familiar with radars. Radars transmit a signal, wait for the echo, and then receive the signal. You could consider a radiometer a receiver only. Much more sensitive. It actually measures the noise of the signal coming in. It is in the noise, and that's where most of the information uh, of the variable is, the geophysical variable in this case is. So on the slide, you can currently see where microwave radiometers sit, shown by that red box, and on the left you have brightness temperature measurements at 19 gigahertz that come out of, in this case, the Earth, uh, and what we see at 19 gigahertz in the microwave regime. All right, so why do folks use radiometers? Well, the most obvious one is we can see through clouds. So compared to our colleagues in IR and visible, we actually peer through the Earth, see several of the Earth's geophysical signatures. Clouds don't affect us, and if they do affect us, we want them to affect us. In 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 the case of cloud top ice scattering or precipitation. So you'll find that microwave radiometers are sensitive to several of these aspects, depending on which frequency you're using. In fact, the plot on the right, courtesy of Steve Swatley from NRL Monterey, shows you the impact that microwave observations have on weather forecast prediction. So the third bar there says Leo microwave, and the x-axis is percentage of error reduction depending on the observation type. And you can see that by far microwave has a major impact in reducing the error of our weather forecast predictions. So microwaves in general are very useful for us. We many times may not see it in our day-to-day activity, but we all rely on weather forecasts, and microwaves have a big part to play in that. Again, this might be going a bit too basic, but just for folks who might not be aware, or would like a recap of what actually gets measured. Um, Planck's law tells what the brightness emission from a particular body at a particular temperature might be. That's the plot on the left. You can see at different temperatures, you have these brightness emissions coming from different temperatures. The x-axis shows what frequency they come at. So, for example, the Earth, which is more or less around 300 Kelvin, it peaks right around the infrared. So most of our Earth's emission comes in the infrared. Similarly, the sun, which is somewhere around 5 to 6,000 Kelvin, you'll notice the peak is right around infrared to visible. So that's where the most of the emissions come from. But it actually emits across the spectra. So the Earth emits in microwave, IR, visible, everything. The Planck's law talks about a perfect black body. A black body is a perfect absorber emitter, and if it were a perfect black body at that temperature, what would its emissions be? That's shown by that frequency below. You can see brightness on the left, and the T on the right side is the physical temperature that dominates it. So where does microwave come in? We come as an approximation on one side of Planck's law, which is called the Rayleigh-Jeans law. It's an approximation on one side of the Planck's law. So if you simplify the Planck's equation, you get the Rayleigh-Jeans law, which directly relates brightness temperature being proportional to physical temperature. So that is the principle that microwave radiometers operate at. You measure the emissivity of a signal, which in this case is, another way of putting it is, what would this body, this geophysical variable, emit compared to a perfectly emitting black body. So you take that ratio, you get your emissivity, and that emissivity inherent to it has a lot of the geophysical parameters. Like salinity has a certain emissivity, so it emits a certain value, which when compared to an ideal black body, you can actually back out what the salinity of that signal might be. So microwave radiometers work in the Rayleigh-Jeans regime, and again, there's brightness temperature to temperature proportionality that we take advantage of to measure emissivity to get the geophysical variables. So what geophysical variables are we talking about? This is a pretty good plot. It's from the National Academies of Science, Engineering and Medicine Handbook on Frequency Allocations. The y-axis is sensitivity, delta TB to delta P, P being the physical parameter that you're interested in. And then the x-axis on both scales are frequency. In both cases, they go in go from 0 to 40 gigahertz. And then the curves are normalized curves. So let's just pick one, for example. On the left side, if we took the purple line, right around 22 gigahertz, you'll see the peak to integrated water vapor. What that's telling you is we are most sensitive to integrated water vapor at 22 gigahertz, which makes sense because it's a water line. Similarly, if we were to go to soil moisture, which is the yellow curve on the left, we are most sensitive in the lower frequencies, around 1 gigahertz or so, and then our sensitivity to soil moisture goes down after that. If we look at its complementary surface roughness, which is, several soil moisture folks always worry about surface roughness. Surface roughness has its least sensitivity in the low gigahertz regime, but it keeps going up, which makes sense if you think about surface roughness. The plot on the right is also very similar. In this case, we're talking about salinity, which is the green curve. Again, a lot more sensitive early on, and then completely loses its sensitivity by the time you're on 6 to 7 gigahertz. Sea surface temperature, sensitive around 6 gigahertz. Wind speed, you keep increasing your sensitivity as you go up, and it's sensitive after 10 gigahertz. Again, you can see the same water vapor line or integrated water vapor as the left plot on the purple. So you can see, depending on which frequency you are, we're sensitive to different geophysical variables. These geophysical variables emit a certain emissivity that is a function of that variable, how much water there is in the cloud, how much water there is in the atmosphere, how much salinity there is in the ocean, how much moisture there is in the soil, how much roughness is there on the sea surface or on the surface, soil surface. All of that is inherently a part of your dielectric, your emissivity, that then emits a certain value that is less than the black body, and then that tells you what the contribution of that particular variable might be, and that helps you back it up. Here's another example similar to the last plot. In this case, we're actually going from 1 gigahertz all the way up to 200 gigahertz. And as I said, we're we're sensitive to salinity, sea surface temperature, wind vectors at the start around 10 gigahertz, water vapor around 22 gigahertz. But if you start going into the 50 gigahertz region, you can see the oxygen complex right there. If you go further up, you get more into atmospheric sounding temperatures around 118, 183 gigahertz, which is uh, sensitive to oxygen or water vapor. In fact, you could use those lines and everything in between to back out planetary boundary layers. So there's several things across the spectra that we're interested in, which is why most radiometry folks work in all frequencies. In a way, they're interested in everything. Here's an example of soil moisture and salinity. This is a video. Let me see if I can play this. All right. So you can see soil moisture and salinity having the structure behind it. The color on over the ocean shows salinity. The color over land shows soil moisture. You can actually see on the bottom right of that there's a time scale, so you can see the seasons, the winter, summer seasons going up and down, precipitation events coming in, outflow from the Amazon plumes, precipitation events hitting India, and then coming out of the Bay of Bengal. So it's very interesting, and it's measured in this case at L band. So I just wanted to give this example as another um, key measurement made by radiometers. In this case, currently we have two missions up there. The SMAP mission, which is Soil Moisture Active Passive, which is a NASA mission, and then an ESA mission called Soil Moisture Ocean Salinity, both of which are at L band that measure these things. The plots on the right show you the sensitivity of your brightest temperature to the parameter. So if you look at the top right, as salinity goes up, your brightest temperature goes down. But you can see at different water temperatures, you have different sensitivities to it. So we're not as sensitive to colder waters, but we're very sensitive to warm tropical waters at L band. Similarly, bottom right has soil moisture. So the x-axis is volumetric moisture content in the soil. Y-axis is brightest temperature, and again you can see as the moisture content increases, brightest temperature decreases, and this depends on what soil type you have as well. The next one I want to show is sounding. There's a reason I'm showing these examples, because when I start talking about spectra, you'll see where we are currently and then where we want to go eventually and what's impacting us making these measurements. So the next one is sounding. So as I said, there's a 22 gigahertz line, there's a 55 gigahertz oxygen complex, there's a 118 gigahertz oxygen line, there's 183 gigahertz water vapor line. Depending on which channels you choose, which are shown by the black dots on the left screen, you actually sample different heights of the atmosphere, which is shown by the right plot on your screen. So depending on which frequency you choose, you are sensitive. Those are weighting functions across the atmosphere. So you're most sensitive to that part of the atmosphere. So just for example, 57.95 gigahertz is most sensitive at 80 millibars. And then if you go further to 50.3 gigahertz, you're sensitive mostly to the surface emissivity. So depending on which frequency you choose, you can actually sample the full atmosphere and get a full sounding profile of the atmosphere. In this case, this would get you oxygen or temperature profile. This is another example in which case I'm showing you water vapor. So depending on where you are with respect to 183 gigahertz plus or minus 1, 3, 7 gigahertz, or you go to 166, you similarly sample different regions of the atmosphere. In fact, the plot on the right is the best example of what you see at different frequencies for the same Earth. Starting at the top, we have 87 gigahertz, and then 164, 174, 178, and 181. And you can clearly see that as you go from, let's say, for example, 164 to 181, you're seeing some part of the surface, and you're going farther and farther up, and you're seeing more and more on the top of the atmosphere. Uh, this is not just useful for sound. You can also use this for tropical storms, where depending on the frequencies you have, you can either peer deep into the tropical storms or right up at the top of the tropical storms, back out these warm convections that happen within tropical storms. And this plot's a very good example of one of the storms that hit LA in 2022, I want to say. Um, you can see the difference at 34 gigahertz versus 165 gigahertz for the same storm. So with this, I'd like to sort of conclude the first part, which is the usefulness of microwave radiometers, the number of frequencies we use, the different reasons we use them for salinity, soil moisture, wind speed, um, atmospheric sounding, planetary boundary layer, all of these different things, um, and how we're passively getting the emissions from there. There's no active signal being sent here, so all of this are passive microwave emissions that in this particular plot, for example, the storm itself is sending the the water particles or the cloud droplets or the top layer ice is sending back towards your remote sensing instrument. So that takes me to the second part, which is the shrinking spectra. So passive microwave either operates in something called a protected primary allocation, where by government regulations, international cooperation, you cannot emit anything in that regime, or a secondary allocation where it's not necessarily primary, you're not the sole occupant there, and other frequencies might exist within that allocation. Why is this very critical for radiometry? It goes back to what a radiometer is. It is measuring the emission from the Earth. It is just a receiver just listening to the Earth and microwave. So it is already measuring in the noise level. We're talking about something like I might get this number wrong. I think something like minus 70 dBm per hertz or something like that. Don't quote me on that number. So you can see it's already at the noise level. Any active signal, any other source within that spectra, even a couple of milliwatts, if it's looking straight at the remote sensing antenna, or let's say it's looking away but it has a large side lobe, can completely blanket out the original geophysical signal that you're looking at. So spectrum protection is an important thing, and it's getting crowded. There are good reasons for it. Obviously, we're not the only folks who need Spectra. There are colleagues in the communications regime also need this, um, and other industries. So it's this cooperation that's an ongoing thing. It never ends. You just have to keep working with colleagues across the table to ensure that everyone's interests are met, um, and that's one of the things that I want to talk about going ahead. So spectrum allocations. So if you look at this plot, there are 7 subplots. It's from the National Academy of Science Committee on the Views of Work 2023. That's where this plot's from. And for example, the top plot shows you from 30 kilohertz to 300 kilohertz. The second top plot shows from 300 kilohertz to 3 megahertz, then 3 megahertz to 30 megahertz, so on and so forth, all the way up to 300 gigahertz. So this is more or less your microwave regime. Now, within that, if you look at the green bars, uh, that is the only allocation that Earth Exploration Satellite Services, sorry, that is the only one that radio astronomy has. And if you look at the orange bars, that is the only one that EESS services have. So you can see there's not a lot allocations there. By the way, the text is slightly wrong. It should say orange in the text. But the point is, there's already limited regimes where you can make these measurements. For example, if you go to the bottom plot, you can see orange around 50 gigahertz. That's important, right? 55 gigahertz, that's where the oxygen complex is. There's no other place where the oxygen complex, at least that oxygen complex, it won't move for us. It exists. It's science. So it's physics. So it has to exist there. If it gets encroached on, we don't have an option like, oh, you know what, we'll just go to up to 70 gigahertz and measure the oxygen complex. You can't. It's 55 gigahertz, the only place it is. If we go from the third from the bottom, at 1.4 gigahertz, I was just talking about L band for salinity and soil moisture. You'll notice at 1.4 gigahertz, there's an allocation. Those That's the hydrogen line, 21 centimeter hydrogen line that radio astronomers use, and then we use for soil moisture. So you can see there are only certain lines that you can measure at, and if it gets encroached upon, that becomes a problem for you because you can't actually get to the science you want. So we do have spectrum allocations, but they're getting squeezed in, which is a concern for remote sensing folks. And what happens if they get squeezed in? So this is a great example. This is the SMAP mission. What you're looking at is radio frequency interference. So blue is good. That means there's no interference. But anything above blue, that means there is occasional interference that happens. Red means there's interference there all the time. And let me play it again. And this is L band. This is 1.4 gigahertz. This is by far technically protected across the board by all international regulations. Yet you can see that reality isn't the same. Even though there are regulations protecting it, you can see that it is inundating RFI in certain regions. A good example here is Japan. If you look at Japan, it's completely red. They um, they had RFI coming in from I believe it was IF signal, and you can see it just completely takes away any L band measurements in that region. And what the consequence of that is, we can't measure soil moisture in Japan using SMAP. This little region around Myanmar or Bangladesh just popped up at the end of 2023. You can see there's a lot of RFI around the Russia-Ukraine region. I don't have to tell you guys why, but even in general, there's a lot of RFI in Europe, and what the consequence of that is when our remote sensing satellites pass over, it's not just that point that's lost. We pick up these signals from the side lobe. They're just high enough that you can't detect these RFI sources, but just low enough that they straight up impact your measurements. So this is what happens when there's possibly regulation, but not enough enforcement. Here's another interesting example. This is courtesy David Draper. I love using this plot. I show it almost at every talk I give. And it's another consequence of incomplete spectrum protection at C and X band. And what you can see, especially over the continental United States, is this band or halo around the United States, which is our direct TV or satellite broadcast, satellite cable broadcast that is in geo, illuminating CONUS, and it's at the right complementary angle to where our remote sensing satellites are, and the signal just bounces off, in this case from the ocean, and comes in the mission. And the scale got cut off there. Red means about 30 kelvin. So that's a very powerful signal. what that immediately does is it takes us away from doing any coastal science over the ocean that we potentially could have. The band in the middle we believe is reflection off of snow. So you can see the straight impact that incomplete spectrum protection might have on the system. So there's a lot of value in spectrum, and again, this isn't. I want to make sure this isn't us against them. There's obvious need for getting wireless dominance, 5G dominance, but we can't ignore that there's sometimes a penalty to be paid as well, right? So here's a good example where a little tiny band was auctioned off for like $45 billion. Um, there's a lot of interest from a lot of folks in these limited resources, because it's like real estate. There's only so much spectra to go around. Recently, there was some concern around the 24 gigahertz spectrum where FCC auctioned it off for 5G. And if you remember, I showed you the water vapor line around 22 gigahertz. So the closer you get to those lines that are important, it might impact your weather forecasts. So this is a good example where NOAA and NASA sort of said, hey, you know what, this if you auction off 24 gigahertz, it might impact us, but the FCC auctioned it off anyway. So again, I just want to make sure this is not us against them. This is more of we all need to work together. Uh, if we lose spectra from a science perspective, chances are we'll lose capabilities forever. So there's a balance to be played here that we all need to keep in mind. Spectrum is valuable and limited. So what have folks at across the country, actually across the world, trying to do? We're trying to build architectures that can not necessarily completely live with RFI. If a signal's corrupted with radio frequency interference, it's corrupted. But you try your best to be as resilient to it. So, for example, this is a good example of if we get a strong RFI signal, we don't want our system to go into nonlinearity. We want to keep preserving the nonlinearity till a point we can't. So at least try and get those little bits of information that you can before nonlinearity completely ruins the signature. So in this case, so the example of an RFI resilient radiometer architecture, it's a pseudo correlation radiometer where if any nonlinearity happens, it happens to your signal and your calibration signal, and hopefully that balances that out, which is the plot shown in the to your right, where you can see things are linear, and then between the green and red dashes, the signal goes nonlinear, but the calibration stays flat till a point where you can't do anything and everything just goes off nonlinear. So these are games that we're trying to play because we sort of know that it's a limited resource and we have to keep protecting ourselves. There are other things for the past I want to say now 2 decades. Several RFI filtering algorithms have been generated that are either temporal in nature, spatial, polarimetric, spectral, statistical, or a combination of all of these. I want to be clear, these are RFI filtering algorithms. These are not RFI mitigation algorithms. We cannot uh, detect RFI, excise it, and then replace it with a clean signal, because we still don't know what the level of that clean signal is. So the best you can do is hope to capture RFI and flag it, but you can't fix it. Right. So as I was saying, if you look at the plot on your top left, that is an RFI corrupted signal, and it's from SMAP. And we've tried to implement a lot of these algorithms on board so that you can actually fix these RFI signals. If you look at the plot on the top left, it suddenly looks cleaner, and I almost want to use air quotes here. RFI was detected and excised, but there's still a lot of red spots there that you don't see in this plot resolution, but does affect your data. Plot on the bottom left is this CubeSat called Qbert that was launched 2018 that had these wideband RFI detectors, and it clearly showed between the blue and the red uh, the potential of doing real-time RFI filtering. A good consequence of this was we started implementing these complex algorithms on digital backends. We started implementing these high-end spectrometers on digital backends that not only helped us with RFI, but actually we started using for science itself, which is the plot on the right from one of my colleagues, Juan Francisco Munoz, where we use these digital backends, these spectrometers to actually measure the full spectra. So again, I was talking about the 50 gigahertz oxygen complex. The plot on the right is the 50 gigahertz oxygen complex. Each of those lines is one of the oxygen lines that now we can measure because we've implemented these as a sort of side consequence to uh, having these RFI filtering backends. All right, so I talked about the ever shrinking spectra. Now I'm going to sort of the last uh, 7 or so slides, I'm going to talk about the expanding needs. Spectrum is going down. It's quite clear, and it impacts science. That limits us to the bands that we're measuring in already. But the thing is, just due to physics, that just because you're measuring in those bands doesn't mean there isn't information outside those bands. And there is a high potential for new science beyond just those traditional radiometry channels that we hopefully might be able to take advantage of. Here's a good example. This is salinity on the left. The x-axis is frequency, the y-axis is sensitivity to salinity. So the higher it is, the better it is. Tropical waters are around 30 degrees C. You can see the blue line. And as soon as you go from tropical waters to polar waters, your sensitivity reduces by a massive factor. This is just the nature of things. The little brown box shows where the 1.4 gigahertz currently measures. If you went lower in frequency or expanded your frequency, you can actually see the green and the red line on the left plot actually go buying back that sensitivity as you go lower in frequency. So there are advantages to suddenly being able to measure, say, polar salinity if you were able to measure wider frequencies. Plot on the right is a similar plot to what I showed earlier, which is a sensitivity to frequency for different parameters normalized. And the interesting thing here is if you expand your bandwidth, you can actually get all of these different geophysical parameters in one go. And in fact, they're orthogonal to each other, so you might not even need ancillary information. You can actually solve for different equations at the same time. So the point here being, there's the potential to lead to new science that we don't have if you expand your spectra. It's a drop in sensitivity we're talking about. This is at higher frequencies. So I just talked about L-band. If we talk about frequencies wider than that, look, we only measure 8% of the total microwave spectrum. Some of it was limited by initial analog designs, and you have to pick and choose your frequencies, and some of it was limited by the spectrum allocation you have. You can see the gray, the orange, and the purple showing different limited coverages that you had. The blue line is your brightest temperature over frequencies. And there is an untapped potential here. If we go from that 8% to something represented by the green line, you could potentially measure the whole spectrum and open up new science. And what would that new science be? In this case, right now, NASA, for example, is very interested in planetary boundary layer. It's a very difficult measure. And planetary boundary layer is like the top 1 to 2 kilometers above the Earth's surface, where most of the Earth's dynamics happen. Obviously, humans are connected to it, but measuring it from remote sensing is very hard. I showed you those atmospheric weighting functions. You can measure most of the atmosphere, but as soon as you get closer to the surface, well, the surface emissivity becomes a issue. But what if you could expand your frequencies? I could expand frequencies not only that measure higher up in the altitude, but measure lower down in the altitude, and then use a combination of all of those frequencies to actually figure out what's generally going on in the atmosphere and around the PBL. So the top left plot is an example of that. Red means high sensitivity, blue means less sensitivity. The x-axis is frequency, the y-axis is altitude. So you can see at say 118 or 183, you have sensitivity to up in the atmosphere, but as you go around it and go between it, you start getting sensitive to stuff lower in the atmosphere where the PBL resides, and that's kind of what we're going for. You want the full spectra, which is shown by the bottom left plot. The shape of the spectra might be able to tell you where the PBL is. So there is push, at least amongst at NASA and JPL, to do these ultra wideband signals so that we can detect not an easily detected signal PBL globally. How are we doing it in terms of technology? We're sticking to our RF roots, obviously, because you need the RF signal to come in at the frequencies that you want them, somewhere around 50 to 183 gigahertz. But we're playing with bandwidth by working with photonic signals, or these, in this case, this is from our colleagues at uh, Phase Sensitive Innovations and Sandia National Labs, who've built these photonic chips that can take in these wide 50 gigahertz signals and then channelize them in a gigahertz resolution over only about a 1.5 centimeter by 1.5 centimeter chip, so that we can get those bandwidths and do that. So, all right, so ever shrinking spectra, ever expanding needs, and you can see that's sort of those two contradictory needs have resulted in a need for new receivers. Uh, and photonic is obviously one of them. This is an example from the photonic chip measuring 1 gigahertz signals across the band. Uh, and then, it doesn't just help you to have a back-end photonic that can combine all of these signals. You still need to measure the whole signal at the front end. So what do? Colleagues at Northrop Grumman are currently working on being with JPL on being able to compress these wide signals into a single front-end receiver, 20 to 200 gigahertz. So there's a lot of technology work that's happening. This is not the purpose of this tutorial here. I just wanted to give an example of where the future is for microwave radiometry. And, with that, I'd like to summarize this short tutorial. You can see radiometry serves a variety of scientific applications over all domains: ocean, atmosphere, surface, cryosphere. Interference is an increasing concern for us, and at the same time, we're not letting that stop us from expanding the potential science that we can derive. So the community is hard at work on balancing protecting spectrum, yet trying to extract more science for the future. And with that, hopefully this tutorial was useful for folks. I I am always open to questions. Folks can feel free to email me at my name, siddharth.misra@jpl.nasa.gov, and I'd love to have a discussion or get your thoughts about this tutorial. Thank you very much.